So this chapter is called work and energy. So basically, what we are trying to do. In the previous chapter, we introduced Newton's law. Newton's law actually tell us everything. It is the law in classical, of course. If we're looking at classical physics, it's the law that govern how things move. So if we know the forces, we know the mass of the object, we can find its acceleration, and from the acceleration, we can find the equations of, or write the equations of motions, so we can predict what the object is going to do. Even if we have a system of multiple objects, we can divide them into parts and deal with each part alone, or each object or each particle alone. Now, there are two points that kind of limit not our theory, but our practice of the theory, our practical applicability of the theory. The fact that Newton's law is a vector equation, and dealing with vector equations can be bothersome in many cases. So we have to pay attention how we apply them. We have to choose axes, etc. So we have to deal with vector equations. The second thing is that if our forces are position dependent, then our acceleration is going to be position dependent as well, or time dependent. So if we have a variable force, not a constant force, we're going to have also a variable acceleration, and this lead to complicated equations of motions. They are not solvable. We can solve them in many cases using calculus, but they are a little bit bothersome. So in this chapter, what we're going to do is we're going to introduce a new concept, a concept of work and energy that is actually based on Newton's law. We're not going to, everything is going to be derived from what we know about Newton's law. But this actually allow us to deal with the scalars instead of vectors, and also to deal much easier with position dependent or time dependent quantities or forces, like for example the spring force. So the force of the spring depend on the elongation of the spring. So let's start with defining this new term that we're going to introduce, which is work. So we're going to introduce the concept of work. So if you look or Google the definition of work in physics, of course, we have to distinguish between the work that we use in physics or we use in general life. So the work in physics or anything in physics has to have a precise definition. So work is a measure of energy transfer. It's not energy, it's energy transfer by an external force that occurs when the object is moved over a certain distance. So if we have a moving object, or an object is moving, and we apply a force on it, an external force, this force could transfer energy to the object. This transfer of energy is the work done by the force. Right. This definition is nice, but the thing is we don't know what energy is yet. So we're going to leave it for a little bit and see how that works. So work is that how we use the other word work. So when we apply a force to a moving object, this force could be doing positive work or negative work. If the force has a component or is in the direction of motion, and the force مع الموtion, then I say that this force is doing positive work. It's giving energy to the object. يعني اذا انا عندي مثلا شيء عم يمشي قدامي ودفشته باتجاه الموشن تبعه, basically I'm making it move faster, so I'm giving it energy. So if the force, not necessarily the complete force, but just a component of the force is in the direction of the displacement, then this force is doing positive work. But if the force has a component, or the component of the force is opposite to the direction of motion, then this force is doing negative work. So it's trying to stop the object. So how do I define it now? So I need a mathematical definition of this quantity work. So I define the work done by a force F. So I'm talking about a specific force F in a certain interval. It has to be defined in an interval between initial position and final position as the dot product between the force and the displacement delta R. So delta R, heat displacement, heat change of position. So I start from initial position R initial. I go to final position R final. If I have a force F applied on the object in this interval, so I go from here to here. So this is my displacement vector delta R, and there's a constant force applied during this interval F. Then I define the work done by F as F dot dr. Now, if you don't remember what is the dot product, let me remind you. So if there are two ways to resolve the dot product. One, by before we get to components, by magnitudes. So I can look at the displacement, total displacement d. So here the magnitude of the displacement and the magnitude of F. Then I project F on the displacement. So I don't take the total force, I only take the component of the force along the direction of the displacement. Let me erase this. So this is F. It's not in the direction of the displacement. I take only this part. This is the component of F along the direction of the displacement. So component, component in the direction of the displacement here. And this lead gives me the angle cosine theta now. It's the angle between the displacement and F. So if theta is between 0 and 90, I got a positive cosine. If theta is 90 exactly, I got 0. If I'm above 90 to 180, I got a negative work. Now, easier to look at it or to calculate it is to look at, choose an axis and look at the components. So I can choose the x-axis and the y-axis, and I can split my dot product into a x component, or a term that comes from the x component, and a term that comes from the y component. So I have fx delta x. So it's the component of f on the x-axis times the displacement on the x-axis plus fy delta y, which is the component of the force in the y-axis times the displacement on the y-axis. Now, if you see in this example that we have here, we don't have delta y, we only have delta x. So we only have this term. So basically, we are taking only the component of the force in the direction of the displacement. But of course, if you want to look at the general formula, we have to keep both terms in there. So this would make our calculation easier. So it depends on the axes we choose. But remember, the rule that we did for axes, if we can choose one of the axes in the direction of motion, then that would make our life much easier. So it would make our dot product much easier. It would make our calculation much easier. So now let's see about this work. So work is a scalar quantity. It's not a vector. It doesn't have direction. It could be positive or negative, depending on the relation between the direction of the force and the displacement. Remember, we are defining the work done by the force F over an interval. So we have to be very specific in that. So we're talking about a certain force, and we're talking about an interval between initial and final position. Work is an interval quantity. Now, the SI unit of work, it's force times displacement. So it's Newton times meter. But we can write this as, or we call that joules. So after the scientist Joule, so we call 1 joule is 1 Newton times meter. If we want to express it in the fundamental quantities. لنيوتن نعرف هي acceleration times mass, so it's kilogram meter per second squared. So يطلع عندي kilogram meter square divided by second square. Now, if we have a non-zero force, there are two cases for that to have a zero work done. يا اما the displacement is zero, so there is no displacement. طبعا no displacement مش معناتها no motion. في انا بلش من نقطة امشي وارجع لنفس النقطة. Or I'm not moving at all. In that case, we have all the forces are doing zero work. Or if the force is perpendicular to the displacement, it means that it has no component in the direction of the displacement. Now, let's look at an example. So let's say we have this 50 kilogram box. We started at x initial, and we want to pull it to x final. So we want to look at the forces acting on this box and see what are the works done by each of these forces. So first, what are the forces? We have weight, vertical downward. We have N, vertical upward. We have tension along the rope that I'm pulling with. So this is tension making angle theta with the horizontal. Then I have friction opposite to the direction of motion. So this is kinetic friction. So I'm going to choose the x-axis in the direction of motion and the y-axis perpendicular to it. So the x-axis is with the surface and the y-axis is vertical in this case. Now, if we look at weight, weight is vertical, motion is horizontal. So weight doesn't do any work. It's perpendicular to the motion. If I want to specify it, I'm going to call it WG, the work done by the gravitational force. حتى ما اكتب WW بس. So it's the x component of the weight times the displacement on the x-axis plus the y component of the weight times the displacement on the y-axis. If I go back to the displacement, that in this case, of course, I chose actually the x-axis in the direction of the displacement. So delta x is equal to a certain distance d plus d. So I moved a certain distance in the positive x-axis because I chose the x-axis here. Delta y is the vertical direction now. So it has no displacement on it. So delta y is 0. Now if I come to the to the weight vector, I can split it also into two components, wx and wy. Now we look at the weight. The weight is on the y-axis, so it has 0 x component. On the y-axis, it's actually in the negative y-axis, so it's minus mg. So when we come to find the work done by gravity, not by gravity, by the gravitational force, we have the x component times the x displacement, but this is 0, so the whole term becomes 0, times the y component multiplied by delta y, but this delta y is 0, so we got 0. Similar for n, the work done by the normal reaction. So if we're moving parallel to the surface, the normal reaction is always perpendicular to the surface. So in many cases, whenever we're moving parallel to the surface, the normal reaction does 0 work حتى لو السيرفس كان inclined. اوكي؟ لانه normal reaction على طول بتكون perpendicular to the surface. Now we come to friction. We have only displacement on the x-axis, so I'm going to only include the x term. So we have the component of the friction on the x direction times delta x. Now, Fr x is in the negative x direction. So we have minus Fr delta x, and the delta x I can replace it by d if I want to write it in components. Now, when we come to tension, again, we have the general formula Tx delta x plus Ty delta y. But I want only to take Tx, so it's Tx delta x. So tx هي الاكس component. So when I project on the x-axis, I have cosine theta. So it's t cosine theta delta x. So now let's put things together. I can look at the net work done on the object. So the net work is the work done by the net force, or the total work done on the object. So how can I calculate this? The net work, I have to take F net and multiply it by delta R. F net, when I found F net, I had to do what? I had to do a vector sum of all the forces. But the properties of the dot product is that I can split it. So I can say that F net here, F1 plus F2 plus F3, whatever forces I have, dot delta R. So I can expand this bracket. So I got F1 delta R, which gives me the work done by the first force, plus F2 delta R, which is the work done by the second force, etc. So the first thing I did, I changed a vector sum. When I was calculating F net, I had to do a vector sum to a scalar sum. Now I'm adding works which are scalars. They are numbers, positive or negative. So I can add them. Okay, so that's the first advantage I have when I'm dealing with work, is I don't have to deal with vector sums anymore. I directly do with scalar sums. Now that's good, but I have to see what is the meaning of this work quantity. Now displacement هو always in the same direction as the velocity. That's the definition actually of the velocity. Velocity is v vector, at least average quantity, sorry, is equal to dr, the displacement, over the time interval. And the time interval, of course, we know time always go forward. So time delta t is always positive. So delta r and v are always in the same direction. But also we know from Newton's law that the net force is in the same direction as the acceleration. So the sign of the work, of the network, actually give us the relation here in the first between F net and delta R. And here the relation between A and V. So, and we know that if A and V are in the same direction, the object is speeding up. عم يسرع. If A and V are opposite, then the object is slowing down. If A and V are perpendicular to each other, then actually we're only changing direction and we are not changing speed, like in the uniform circular motion we talked about last time. So this actually, the sign of the work, give us what's happening to the object. If the net work is positive, then the object is speeding up or its speed is increasing. If it's negative, we are slowing down. And of course, if it is zero, then we are moving with a constant speed, or we are not moving at all. So that's the main use of work now. So work is going to tell us how, not the velocity, because we lost the information about the velocity. It tell us only about the speed, الماgnitude of the velocity. ليه؟ لأنه أنا استغنيت عن الفاكتورز، يعني استغنيت عن الدايركشنز. So of course this thing has an advantages and disadvantages. The advantage is now I'm working with scalars and I can tell about the speed of the object. The disadvantage is I lost the information that I had about the directions. So let's look at two examples that are common. First, the work done by gravity or by the gravitational force. I have to change this, the gravitational force, not the gravity. Okay, so it's the weight. We know that the weight, the force exerted by the Earth on the object, is always directed vertical downward. So it has a fixed direction no matter what the object is doing. So the work done by the weight only depend on the vertical displacement, because it is vertical. What matters to us is the vertical displacement. So if we have a ball that we are throwing it up in the air, and we choose the y-axis vertical, so this is يمكن احنا نسمي الواي axis مش vertical، بس هون انا عم بحكي عن ال vertical direction. So this is the vertical axis. Okay, so I have to be specific that I'm choosing the y-axis vertical. Then weight, the component of the weight in the vertical direction is minus mg. So I have minus mg delta y, and delta y is what? It's the vertical displacement. So when I throw the ball, on the way up, delta y is positive. So the work done by g in this interval. So الانترفال على طول بدي احدد الانترفال، انا عم باخذ الانترفال من هون لهون. And I'm looking only at the work done by the gravitational force, by weight. So this is negative work done. If the ball is falling now, I'm taking this interval from here to here. So this is my displacement. This is delta y2. Okay? So delta y2 is negative, but I have a negative sign here that comes from the force. So the work done is positive. If I take the whole interval from here all the way to here, then there is no displacement on the y-axis. I have displacement on the x-axis, but that doesn't matter because the work done by gravity depend only on the vertical displacement. And that means that the work done is zero. So there is no change in speed, but there is a change in direction. كان البول عم يطلع طلوع هون، شو صار عم يعمل هون؟ عم ينزل نزول. So the work doesn't tell us about this change of direction. It only tells us about the change in speed over an interval. Of course, هون this is if we're looking at the work done by gravity. If the weight is the only force, then we can tell that. If we have other forces like air resistance or something else that is affecting the ball, we have to include them before we find how the velocity, or sorry, not the velocity, the speed is changing. Now, the other force or the other situation we look at is when we have uniform circular motion. So when we are in uniform circular motion, like the moon going around the Earth, the net force is centripetal. It's toward the center. And the velocity in any part of the interval, مش ضروري أنا أكمل سيركل كاملة، حتى لو باخد interval من هون لهون. So in this arc thing, the velocity and f are always perpendicular to each other. So the displacement and f are perpendicular to each other. So the net work done is zero in all parts. هلا اذا انا رجعت لنفس النقطه اكيد ليه، لانه الدلتا ار صارت زيرو. So net work done is zero. But حتى لو ما رجعت لنفس النقطه، لانه الفورس in all parts of the trajectory is perpendicular to the displacement, then the net work is zero. That's why the moon can go around the earth indefinitely without losing or gaining energy. لو the motion of the moon around the earth requires energy, can هالenergy, no matter how big it is, eventually it would goes to zero and the moon is gonna fall toward earth. Same with the earth around the sun. So these motions, because there's no friction, no resistance to them, they actually requires no energy. So the energy, they have energy because they are moving, but it is a constant energy. It doesn't increase or decrease. So they had this energy from the beginning and it stays there as they move around. طيب قلنا انه النتورك بيقول لي اذا السرعه بتزيد ولا بتقل. So I need to know how much it's increasing or decreasing. So I need to write a mathematical equation that relate the change of speed to the work done on the object, the net work done on the object. I do that using Newton's law. So I'm going to take an object that has a net force on it, F. So I choose the x-axis, the y-axis, whatever axes I need. I can say that the network is equal to Fx delta x plus Fy delta y. But Newton told us that F equal to ma. So Fx is equal to max and Fy equal to may. Now, I can write the equation of motion for that. The equation of motion relates to me the acceleration times the displacement to the change in the square of the velocity. So on the x-axis, we have ax delta x equal to half vx squared minus v0x squared. So this is initial, if you want, and this is final. Remember, the work is an interval quantity. I always taking initial position and final position. So I'm going from here to here. So I have here x initial and y initial. I go to x final and y final, whatever these. Or this is y. This is x final and y final. So this is my delta r. From chapter 2, and if you need to ask me about it, let me know. So this is when we have a constant acceleration, but the equation that we're going to derive actually applies even if we have a variable force. So I can write the same for the y component. Now I bring all these together. The first thing I do is I replace f here by ax, and then we have ax delta x. I replace it with half vx minus v0x, vx squared minus v0x. So, and I rearrange it. So عندي هون x squared, عندي هون vy squared, عندي هون minus v0x squared وماينس v0y. So بحط الفاينل مع بعضهم والانيشال مع بعضهم. So صار عندي half m vx squared plus vy squared minus half m v0 squared plus v0 y squared. So I took the minus sign common. Now this vx squared vy squared هو magnitude of v. So this is v squared. So it's the final speed. بطلت عم بحكي عن velocity, بس عم بحكي عن speed. So it's v squared. And of course, this is the same, but at the initial position. So the network give us half m v squared minus v0 squared. But I wrote it in this form because we recognize this term, this half mv squared. We know this. We call it the kinetic energy, K or Ke if you want. So this is the kinetic energy. So I can say that the work done on the network done on the object in any interval give us the change in kinetic energy. And of course, the kinetic energy is the energy that is associated with speed. So if you want now, I'm defining my energy. I'm defining my kinetic energy as half mv squared. And this brings us to the first statement we said about work. It's the energy transferred to the object. So now when I do positive work on the object, I'm increasing its kinetic energy. When I do negative work on the object, I'm decreasing its kinetic energy. Now, let's look in details to this kinetic energy, the half mv squared term. So the kinetic energy, the energy is associated with the state of motion of the object. The faster I'm moving, the greater the energy is. And when the object is stationary, it has zero energy. But the other thing about it is this m. It depends on the mass of the object. So if we have a small object that is moving, it would have a certain energy. But if we have a large object that is moving, it would have a much larger energy. So depending on the mass. And this brings us also to this idea that mass is the resistance to the change of motion. So if I want to increase the speed of an object from 0 to 100, I need to give it energy. But the energy I need to give it to is proportional to this v square thing, but it's also proportional to m. So if I want to make an object move or change its motion from 0 kilometer per hour to 100 kilometer per hour, the energy that I need to do, the work I need to do, delta K, is proportional to the mass of the object. Remember, the work is the change in energy. And in physics, we care about changes. We don't care about the energy itself. As I told you, the moon is rotating around the Earth. Its kinetic energy is not changing. So there is no work done. When do I care about the energy of the moon is when the moon, for example, if the moon falls toward the Earth and it hits the Earth, it's going to stop. Its kinetic energy is going to change. It's going to go to zero. So this energy is going to be released in other forms. And this form would be the destruction of the whole Earth. But we'll leave that for billions and billions of years to come. So the network on the object is equal to the change in kinetic energy. It's K final minus K initial. So this is just the show how the force, if I put a force in the direction of the velocity, it would increase the kinetic energy. It means it increases V final. So now we have this formula that we can use. Instead of applying Newton's law, we can use this formula. The thing is, we lost two pieces of information in this, if you are using this formula instead of Newton's law. We lost the information about the direction. So we know that if we do positive work, we increase the speed, but we don't know about the direction of motion. We also lost information about time. Work is an interval quantity between initial position and final position. But going from the initial position to the final position requires time. So we don't know how long it takes using this formula. We know how fast it's moving, but we don't know how long it takes. Because, of course, to do that, we have to go back to the acceleration, because the acceleration is delta V over delta T, so we can know what is the time interval. Let's apply our knowledge into a problem. So of course we can solve these problems using Newton's law because these are simpler problems, but let's solve them first. Let's solve them using the work energy theorem. So a box is sliding on a horizontal floor with initial speed of 2 meters per second. If the coefficient of kinetic friction between the box and the floor is 0.3, how far does it slide before it stops? So أنا جبت box or whatever object and I pushed it on the floor and I leave it. So I'm not pushing it anymore. So I give it an initial velocity 2 meters per second and I left it on its own. Now, when it's on the floor, when it's sliding on the floor, there is weight on it, there is normal reaction of the floor, and there is the kinetic friction force. So if the object is moving to the right, the kinetic friction is to the left. So I want to find the distance where the object stops. I could use Newton's law. I could find the acceleration, and then I apply the equation of motion and find the distance. But let's say we want to use the work energy theorem. So initially, the object is moving with the velocity v. So we have v initial. Let's write it with the vector. So it has a kinetic energy initial. هلا اذا بدكم let's call kinetic energy ل ke like they used to call it. هلا k is also the kinetic energy. It's easier to abbreviate it with k. So ke is equal to half mv initial square. We don't have a vector anymore. Now we have to go to the final situation. At the final situation, the v final, I want the object to stop. So v final is 0. So kinetic energy final is 0. So now I can apply the work energy theorem. So W net, the net work done on the object, is equal to the change in kinetic energy. But we know that W for any force depend on the displacement. So from the W, I should be able to find the displacement. To find W net, I have to add the work done by all the forces. So I have to have the work done by the gravitational force plus the work done by the normal reaction or the normal force plus the work done by the kinetic friction force. So now the gravitational force and normal reaction are vertical. They are on the y-axis. Let's draw the y-axis here. So I'm going to choose the x-axis in the direction of the displacement. So I only have displacement on the x-axis. So delta x is equal to d, which is I want to find, right? So this is my unknown. And delta y is 0. So this means that the work done by the gravitational force and the work done by the normal reaction are both 0. So only I have the work done by friction. The work done by friction is equal to the kinetic friction is equal minus Fk multiplied by delta x multiplied by d. So if I find the work done by friction, I can find d. So let's replace that in our equation upstairs. So we have W net equal to the change in kinetic energy. So let's rewrite it. So W net equal to delta KE. So that's equal to خلينا نكتبها سطر جديد. محل W net لحط minus F K D equal to final K final minus K initial. So 0 minus half mv initial square. So this leads to d. Well, we still have a problem. We don't know fk. So we need to find what is fk. Well, here we cannot do much with that. Instead we use Newton's law, because we need to know a force. So we know that the kinetic friction is equal to mu k n. So we need to find n. So I apply Newton's law only on the y direction. On the y direction. So al y direction, ay is 0. That's why I can simply apply Newton's law without hardship. So we have n equal to mg. So this gives us, now we go back to the left side equation. So we have minus into mu k mg multiplied by d equal to half mv initial square. So m cancels out, and we find d. So d is equal to v squared, v initial squared, over 2 mu k g. So mu بلا. So this is the final answer that we're looking for. So let's see if this makes sense. If initially the block was moving fast, or the box was moving fast, it would take a longer distance to stop. The mu is the friction. Right? So mu is the friction component. The stronger the friction coefficient, the faster it's going to stop. So it would go shorter distance. And it's inversely proportional to G, because G is telling me how much I'm pressing on the floor. And remember, friction depends on how much I'm pressing on the floor. But the mass cancels out. Why the mass cancels out? Because it comes in this, how much I'm pressing on the floor, it comes in the N equal to mg term, but it comes also in the term of the kinetic energy, because what matters at the end is not how fast, it's how much energy I have. And the kinetic energy, not only v squared, it is mv squared. Okay. I want actually to try something, because I tried it last day and it was interesting. I want to ask this question to, as it is, to ChatGPT, and see how it would explain it. So let me actually send it to us on the group, so I can copy it to my phone. No, it's sending as a picture. I want to send it as text. Okay. And then I will open my phone and copy. Go to ChatGPT and see if, well, we're not going to tell ChatGPT to use the work energy theorem for starters. So let's see how it would solve it. Well, they use the work energy theorem. To solve this problem, we can use the work energy theorem, etc. They find the acceleration Fk over, no, they forgot G. They put it back in here, but they found the acceleration. Let me take a picture of it and send it to you. So this is the ChatGPT solution for this problem. Even though they started with saying that work energy principle, but then they found the acceleration. The friction force is given by UKM. No, it's UKMG, but they didn't explain why, right? So well, you can ask though. You can ask ChatGPT to explain certain parts to you. So then you find A. Okay, and then you apply the equation. Right, let's solve one more problem before we call it a day. So you can still see my PowerPoint, right?
Yes.
Yes.
Okay. So a piece of plastic slide on an incline, as in the figure, starting from rest. After sliding a distance of 1.5 meter, the box has a speed of 3 meter per second. What is the work done by friction? So here we have the box. It started from rest. Slide down the incline a distance 1.5 meter. While it's sliding, there's weight على طول vertical, ما بيتغير الدايركشن للweight. Normal though is perpendicular to the surface. والfriction is parallel to the surface, opposite to motion. So it starts from rest. It ended with a speed of 3 meters per second. So let's write this. Now I'm not going to put the vectors. So V initial is equal to 0. It goes to V final, which is equal to 3 meters per second. This is the magnitude. Now, this means that my kinetic energy initial is 0, and it changed to the kinetic energy final, which is equal to half mv final square. Okay. Now, as I'm sliding, there is work done here by weight, because now weight is not perpendicular to motion anymore. صحيح، لان الوي انا بعدني عم بمشي على الاكس اكسس. So let's write our displacement. I chose the x axis that way. So delta x is equal to d equal to plus 1.5 meter. So plus d. خلي plus d لانه I want to solve it in general. And delta y is 0. طب بتقولوا لي انت طب كيف عرفت how delta x والdelta y؟ انا عم بختار الاكس اكسس والواي اكسس. وشو عم بعمل لهون على حالي؟ عم بختار الاكس اكسس in the direction of motion. يعني انا اخترت هيدا الاكس اكسس هيك. down the incline. So let's write here as a note. We chose the x-axis or x direction if you want. Down the incline in the direction of motion. Okay, so that actually kind of specify for us the displacement, but it also specify the components of the forces. So now when I want to find the work done by each force, the work done by the normal reaction بعده perpendicular to the incline, so it has no x component, so this is 0. The work done by friction, the friction force, is still minus fk delta x or fkd. Okay, it is negative, it's less than 0. But now the work done by the gravitational force is not 0 anymore, so it's wx delta delta x. Now wx, I have to see this wx thing, the projection of the weight on the x-axis. الويت بعده vertical, So this is its projection on the x-axis. It's positive. It's in the positive x-axis. It's down the incline, and it is opposite to the angle. And remember, we said that the angle that the weight makes with the y-axis is the same as the angle that the incline makes with the horizontal. So this is equal to plus mg sine theta multiplied by the displacement d. So the net work, W net, is in general, it's equal to the sum of all the works, W n plus W f k is equal to mg d sine theta minus fk d. Now it's equal to the change in kinetic energy. It's equal to half mv final square, not cube, square minus 0. So I want to find, well, they tell me find the work done by friction. Let's keep it as work done by friction. So here plus WFK لأنه بتطلع WFK معنا negative. Okay, so now I can find the work done by friction first. Text box, let's write here. So the work done by friction is equal to half mv square final minus the work done by gravity, which is mgd sine theta. Let's stop here for a minute and analyze this result. So basically, we are gaining kinetic energy. This kinetic energy comes from the work done by weight, by the gravitational force. We are falling down. We're not falling down straight, but we are going down vertically. So the work done by the gravitational force, which is equal, it's positive, and it's equal to mg sine d sine theta, give us positive work. Some of it is going to kinetic energy. Some of it is going to friction, is lost as friction. So friction is opposing our motion. So it's decreasing our kinetic energy. So there's a competition between the work done by the weight and the work done by friction. Of course, we speed up. We went from 0 to 3, so we did speed up. So we kind of lost some energy to friction, but we didn't lose all the energy. Now, if we look at the work done by gravity, تقولوا لي طب ليه ما استعملت هيدي هون الفورمولا اللي عندنا اياها انت كتبت لنا اياها هون اللي هي ماينس ام جي دلتا واي. هون لما كتبنا هاي الفورمولا we insisted that y is the vertical axis. Here in this problem we didn't choose y our vertical axis. Okay, I chose the y perpendicular to the incline. هلا في انا اجي سمي اكسس جديد هون، اخذ هذا الاكسس وسميه شو ما بدكم سموه واي برايم مثلا، هو الفيرتيكال اكسس واي برايم. خلينا نحطه بلون ثاني للاكسس تيبين انه هذا okay. So now I can say that so instead of doing this term, I can say here on the side, I can say that the work done by the gravitational force is equal to minus mg, but not delta y prime. Now on the vertical axis, I'm going a distance delta y. I'm going down first. So delta y prime is equal to minus first. But if you look at this triangle, it's a right triangle, and I'm going, the hypotenuse is d, so I'm going d sine theta. So d sine theta. I replace it in the work done by gravity is equal to, minus goes away, so I got mg d sine theta. So I still get this sine theta term. So see, this is the other thing about work. I'm not restricted by my axes. I can choose axes لكل شغله لحال, لكل force لحال. لأنه at the end I'm gonna get a scalars, and scalars I can add directly. So I got the same term that I got here. Okay. Now, after I got the work done by friction, I can find the force of friction. So if I want to find friction itself, or the coefficient of friction. So first, let's find the friction. So we'll replace minus fkd minus fk d equal to this term all together, and I can divide by d both sides. So I get fk is equal to 1 over 2 m v final square over d. خلينا نشيل هاي ال 2 من هون نحطها تحت, and minus mg d home cancels out sine theta. Now if I want to find the mu, I need to remember that مثل ما عملنا بالproblem اللي قبله, I use Newton's law on the y-axis. So I got mu k is equal to fk over n, which is equal to fk over mg. But I did a mistake here. I forgot the minus sign. So this is going to be minus, and this is going to be plus. And I can find the mu k now equal to, wait, I did something interesting. I taught you how to do your assignments on ChatGPT. Well, you already know that, right? So I just have to cancel m and keep g. But you see, you have this term that comes from the kinetic energy. So this is the energy that goes to motion, and the total energy comes from the work done by gravity. So we're going to get mg cancels out, so we're just going to get sine theta plus sine theta. Makes sense لأنه mu is unitless and sine theta is unitless. So هذا الترم هو, it comes, the second term, it's the term that comes from the work done by weight, who total energy given to the block. Some of the energy went to kinetic energy, and some of it went to friction. So we lost it as heat.
Doctor?
Yes.
Said that n equal mg, but the weight is not on the y-axis.
Oh, you're right. So it's not mg, it's mg cosine theta. So then we have here cosine theta, and I'm بقول لازم تطلع tangent theta. So here we're gonna get tangent theta. هلا ليش ال mg cosine theta؟ لأنه when we apply Newton's law, let's write it. لأنه differ from before. Newton's law on y-axis بيكون في عندي minus mg cosine theta, so it's the projection on the y-axis, plus n equal to 0. So n is mg cosine theta. Thank you for this valuable correction. Clear? Type. There is one more problem here. Let's do that as our what do we call it, the participation grade. So I will send it to you on WhatsApp, and I will open an assignment on LMS for you to submit it. Let me group it as one. In this question, I think I'm ignoring friction. We can do it as well with friction. But for starter, okay. Participation before Tuesday. Okay. We can stop here. Next time we're going to talk about what happens if our forces are not constant. How can we deal with work if our forces are not constant?